In Chapter 9, we're going to be talking about thermochemistry. First, let's go over some definitions. What is thermochemistry? Thermo means heat, so thermochemistry is the chemistry associated with heat. We're trying to find the amount of heat that's absorbed or released during either chemical changes or physical changes. Energy is the capacity to supply heat or do work. We're going to look at an equation a little bit later in this chapter that has heat and work as variables in it, and both of those are just different forms of energy. There are two main types of energy, potential energy and kinetic energy. Potential energy is the energy that an object has based on its position, composition, or condition. In other words, where it is, what it's made up of, and what the circumstances are surrounding it. An example is a ball poised at the top of a hill. It's ready to roll down, and based on the fact that it's at the top of the hill, it has some potential energy. Kinetic energy is the energy related to motion. When the ball is rolling down the hill, that is involving kinetic energy. We're going to use a law called the law of conservation of energy, which says that energy can't be created or destroyed. It can only change in form. For example, between kinetic and potential energy. We could push the ball to the top of the hill, and by doing that, we change kinetic energy into potential energy. Or we could roll the ball down the hill, which would turn potential energy into kinetic energy. Thermal energy is a particular type of kinetic energy because it is an energy of motion, specifically the motion of atoms and molecules. Atoms and molecules are constantly moving around. They're vibrating or jiggling in space all the time, and their state of matter corresponds to how much they are able to move around. Because of their motion, they have thermal energy. Temperature is a related term, but it's not exactly the same thing. Temperature is a quantitative measure of hot or cold. There is a number associated with it. We can measure temperature on a thermometer, and it's going to be directly proportional to the thermal energy. The higher the thermal energy, the higher the temperature, and so on. In the picture, you can see that the hot water has a lot of lines around each of the balls. That indicates it's moving more, so it has a higher thermal energy. And in terms of temperature, we would measure it and call it hot. For the cold water, it has fewer lines around it, indicating that it's jiggling less. There's less kinetic energy associated with it. So thermal energy is lower, and when we measure its temperature, we find that it is cold. Another related but different term is heat. Heat has the variable lowercase q, which is short for quantity. Heat is the transfer of thermal energy between two bodies at different temperatures. Heat is always going to flow from the hotter substance to the colder substance. That is, the substance that has the higher thermal energy to the substance that has the lower thermal energy. You can see that flow of heat in the pictures at the bottom of the slide. The higher thermal energy substance is the one with the red that has lots of lines around it, and it's designated H for hot. Then there's the blue lower temperature substance that has lower thermal energy. Heat is flowing from the hot to the cold, and as it does that, the hot substance gets cooler and the cool substance gets warmer. Heat continues to flow until they both reach the same temperature as each other, which we call the equilibrium temperature. At equilibrium, heat can still flow between the two substances, but it's going to flow back and forth at the same rate. Therefore, there is no net change in heat once it reaches the equilibrium temperature. Both physical and chemical processes can absorb or release heat. When a change releases heat, it's called an exothermic process. Exo means out, and therm refers to heat. So heat is going out in an exothermic process. A reaction or change that absorbs heat is an endothermic process. Endo means in, and therm, again, is heat. So endothermic means heat is going in. On the left, you can see an example of an exothermic process where a lot of energy is coming out of the reaction. Inside the cold pack on the right, there's an endothermic process. Heat goes out of your body and into the cold pack. Since heat is going into the cold pack where the reaction is taking place, the reaction is endothermic. Let's go over some units of energy. One common unit of energy is the calorie, abbreviated little CAL, and it's defined as the amount of energy required to raise 1 gram of water by 1 degree Celsius. Remember, Celsius and Kelvin have the same size of the degree. Therefore, a change of 1 degree Celsius would be the same as a change of 1 degree Kelvin. The calories that you actually see on your cereal boxes or macaroni and cheese are a different kind of calorie, the big C calorie. Big C calories are equal to 1,000 little c calories. In other words, they're the same thing as a kilocalorie, or kcal for short. Another common unit of energy is the joule. A joule is the amount of energy needed to move a 2 kilogram mass, like the medicine ball in the picture, with a velocity of 1 meter per second. A joule is equal to 1 kilogram meter squared per second squared. You'll see those two sets of units used interchangeably. It depends on whether you want to focus on joules or whether we are dealing with things like masses and velocities, in which case we might end up with units like kilogram meter squared per second squared. The relationship between calories and joules is that 1 little c calorie is equal to 4.184 joules. The joule is about 4 times as big as a little c calorie.